Well, good morning, students. Welcome back again due to some technical glitch we stuck in between, and we'll continue with our course in physics, that is the crash course of our Rrb Ntpc and Cpse. So today we'll be dealing with physics. So I've already given a basic introduction about the nature of the questions that are likely to be asked in your examination, and the kind of content that we'll be dealing with. So to start with, let us start with some basic introduction. Let us start with well, we'll start with the basic introduction part. Eraser, eraser, eraser. We'll start with the introduction part. So under this introduction part, we will be dealing with the units and dimensions. So in units and dimensions, you are likely to face 2 to 3 questions in your upcoming examination. So in order to understand these units and dimensions, let us first start with a very popular and a very important term that is known as physical quantity. Alright, so coming to what is called as a physical quantity. So physical quantity means anything that can be measured. Anything that can be measured. I'm unable to see your comments, students, due to some technical error. Alright, so please do not comment anything right now, and pay attention to whatever I teach. We can later deal with that part. Due to some technical error, I'm unable to handle your queries right now. Okay, so right here. Well, so we'll deal what is known as physical quantity. We are dealing with this. So physical quantity is nothing but anything that can be measured. So the key term here to understand is measure. Say if I give you an instance, you go to market, you buy a kg of apples. Alright, you buy 1 kg of apples. So that 1 kg is nothing but the mass of the apples that you have bought. So you can easily measure what are the apples, or the amount or the mass of apples that you have bought from the market, and that pounds to 1 kg. Fine. So that pounds to 1 kg. Alright. So you are able to measure the mass of the apples. So I can say mass is a measurable quantity. Fine. So that means I can say a mass is a physical quantity. Alright. Fine. So if I consider a bottle of water, can you see everybody over here? Say a bottle of water. Hope it is visible to you all. So this is a bottle of water. So I will say here the capacity of this bottle is 1.25 liters. So it has 1.25 liters of water in it. Fine. So that means I am able to measure the capacity of water over here. So that is nothing but the known as a measurable quantity. That is the capacity of the water. That is 1.25 liters of water is nothing but a measurable quantity. Okay. Hope it is clear to you what is known as a measurable quantity. Well, so now this physical quantities now this physical quantity the physical quantity are basically of two types. One we will discuss, that one is a scalar and other is vector. Fine. So in case scalar, it is a type of physical quantity in which we need only magnitude to express them. Alright, we need only magnitude to express them. And in vector, we need both magnitude plus or and direction to define them or to express them. Alright, so in this case, let us take an example in case of scalar quantity to understand. Alright, so if I talk of a scalar quantity example, so if I say you, like I have already defined, say if I say 1 kg of apples, okay, 1 kg of apples. So, and in case of vector, if I say you that a car is moving at say 20 meter per second towards east, okay, the car is moving at 20 meter per second towards east. Now you can see over here that I have written here simply as 1 kg. But here I have written 20 meter per second towards east. You can see that if I say you that a car is moving at 20 meter per second, you probably may be confused that in which direction the car is moving. Maybe not, maybe south, east or west. Alright. So I have mentioned here the direction, and the direction of the movement of the car is towards east. But when I talk of scalar, I do not have to mention any kind of direction. Why? Because I never say that we in fact never refer that 1 kg of apples towards east or 1 kg of apples towards west. Alright, so we can simply focus on the magnitude, that is 1 kg of apples or 2 kg of apples or whatever the mass of the quantity mass of the object that you buy. Alright, so in case of vector, you will always have to find both magnitude and direction. Alright, in case of scalar, you have to simply focus on the magnitude. It doesn't really need any kind of direction to specify. Fine. So at times in you can see a question in your examination that which among the following is a scalar quantity or which among the following is a vector quantity. These are the two likely possible questions that may be asked from the topic that I have just delivered right now. All right. So if you find a magnitude along with direction, it is always a vector. If you find only magnitude and not direction, it is a scalar. Okay, fine. Now let us move to the next part. Well, coming to the next part, let us understand something very important. What is known as SI units. Alright. So now coming to this SI units, SI stands for System International. It stands for System International. Okay. System International. Now System International, what does this mean and why we need this SI units? Alright. So well, so System International, say if I say you buy some mangoes in India, you take it to Britain, you sell over there. Alright. You say that I am going to sell it in kg. Say 1 kg of mangoes will cost you around 100 rupees. Alright. So if you say over that 1 kg, probably everyone may not be able to understand because the unit that they use for measurement is pound. Alright. If the vice versa happens, if some person from Britain arrives one day to your house and offer you mangoes of 1 kg cost rupees 80. Alright. And he will say that 1 pound of mangoes cost rupees 80. You may not be able to understand because you deal with kilogram, gram. That is the unit that you deal on a daily basis. Fine. So that means we need to have a common unit that is understandable by everyone. Alright. So those units that is on an international basis, we take it as a reference or as a common. That means everybody can use that. Alright. So if I say 1 kg, you should be able to understand what does 1 kg means. 1 kg means 1000 grams. Alright. If you say me 1 kg, I should be able to understand that. Alright. So those units that are used internationally, irrespective of any location on this entire planet. Alright. So those units are known as SI units. Fine. So now let us see now let us see these units are basically of two types. One is your fundamental unit. One is your fundamental units and other are derived units. Alright. Now we use fundamental units for fundamental quantities. Fundamental quantities. And derived units are used for derived quantities. Alright, fine. So these fundamental units, now what are these fundamental units? These fundamental units are actually basic in nature. We have some fixed fundamental quantities, so they are basic in nature, and those physical quantities which are derived from these basic quantities are known as derived quantities. Well, the picture may not be clear to you at this current scenario. We'll first deal with the fundamental quantities and gradually you will understand this topic in details. Alright, so let us go to the fundamental quantities first. Okay, so we have 7 fundamental quantities. Alright, we have 7 fundamental quantities. Now let us discuss those fundamental quantities over here along with their SI units, and along with symbols. Alright, so the first fundamental quantity that we will be dealing is mass. So SI unit, we all know it is kilogram. Symbol is capital K small. Second is length. SI unit is meter. Symbol is small m. Third is time. SI unit is second. Symbol is small s. Fourth, we have temperature. SI unit is Kelvin. Symbol is capital K. Fifth is electricity. SI unit is ampere, or you can say electric current also. SI unit is ampere. SI unit is ampere. Symbol is capital A. Sixth is luminous intensity. SI unit is candela. Symbol is capital C small d. Seventh, well students, there is no space over here, so I would move on to the next page. Hope you have noted this down, or later you can take a screenshot of it in the recording part. Alright, the last one, seventh, we have is the quantity of matter. Quantity of matter. SI unit is mole, small m, small e, and symbol is mole, small m, small o, and small l. Alright, so now in examination, the question that may be asked to you is that which among the following quantity or which among the following physical quantity is a fundamental quantity, fine, or which among the following physical quantity is a fundamental quantity. When it is asked, any of these 7 quantities may be present in your option, so you have to select the right ones. Alright, so mostly in examination, the question that is being asked as which among the following is a fundamental quantity is either time or electric current. Alright, but that doesn't mean you have to simply focus on these 2 particular quantities. These 2 have been asked in the previous year, so this becomes important from examination point of view, but you have to still focus on other physical quantities as well. Alright, now let us understand what is derived quantity. Let us understand what is let us understand what is a derived quantity. Alright. So under this derived quantity, so let us consider volume. So volume is a derived quantity. Now how can we say volume is a derived quantity? Let's see. I take a cube over here. So this is a cube I am having. So the length is 1 meter, breadth is 1 meter, height is 1 meter. So we all know volume is length into breadth into height. So volume is 1 meter into 1 meter into 1 meter. So 1 into 1 into 1 is 1 meter into meter is meter cube. As you can see, the SI unit of volume over here is meter cube, and meter cube is taken from meter. So meter is the SI unit of length. Fine. So that means I can say volume is a derived quantity of length. So here volume is a derived quantity and length is a fundamental quantity. Hope it is clear. Is it clear to you all? Oh, yeah, I can see. Oh, I am unable to see your comments over here. Well, so I hope it's clear to you all. Okay. So now let us move on to the next important topic. Okay. So next we will be dealing with dimensional analysis. Okay. So next we will be dealing here with dimensional analysis. Now what is dimensional analysis? Is that when we consider a particular physical quantity, maybe a derived quantity, maybe a fundamental quantity. Now what are the other fundamental physical quantities present in a derived quantity or in a fundamental quantity itself, and in what powers they are present? Dimensional analysis gives us all those details. Okay. So now from your examination point of view, any physical quantity that will be given in your examination will have mass, length and time as its factor. There are also different other fundamental quantities like temperature, alright, or say electricity. They do form a part in dimensional analysis, but in your examination you will always find mass, length and time. Alright, now this scenario will be clear to you once we continue with this topic. Well, I would like to take an example to explain this particular topic. So under dimensional analysis, let us start with the very basic, that is volume. So the derived quantity we have is volume. Alright, so volume we all know it is length into breadth into height. So SI unit of length you will have meter, this is as meter and this is as meter. So finally SI unit I got it as of volume is meter cube. Alright, so when the SI unit of volume is meter cube, this has simply length in it, that is why the unit is simply meter cube and we do not have any other SI unit combined with this meter cube. Fine. So when we are taking length as a fundamental quantity, do you have any mass over here? No. So I can take the power of the mass to be 0. Do you have any time over here? No, you do not have any time over here. So we'll take the power of the time as 0. But yes, we do have length over here. So the SI unit and the power of the length is, we have meter. Meter power is 3. So we have power as 3. Alright. So how do we express this dimensional formula? We have to express the dimensional formula within the square braces. Alright, so in the square braces I will write here m to the power 0 L cube and t to the power 0. So this is the dimensional formula of volume. Alright, so the dimensional formula of volume is within square braces. It is m to the power 0 L cube and t naught. Fine. So now let us take another example to understand this in a much better way. Well, now let us discuss about force. Don't worry if you do not know about force. I will be dealing with this details in our next chapter, that is in the motion or in Newton's laws of motion. Alright, we will see that force under Newton's second law. Alright, we have the Newton's laws of motion. So we have first law, then second law, third law. In the second law, we will be dealing with force. Okay. So force is expressed as a product of mass into acceleration of the body. So in symbolic form, you can write it as F is equal to m into a. Alright. So acceleration is a vector quantity. How it is vector quantity and all, we will see this in our session on Newton's laws of motion. So this is F is equal to m into a. This arrow simply represents that this physical quantity is a vector quantity. Here we have an arrow over force. So force is a vector quantity. We have an arrow over acceleration. So acceleration is a vector quantity. Fine. So now let us see in examination, if it is asked that which among the following is a dimensional formula of the given physical quantity, and the quantity that is given to you may be force as well. Alright, so let us see over here. So let the step number 1, follow some basic steps and you will get your answer. Step number 1, first of all, write down this entire physical quantity, that is force, in terms of its formula, that is F is equal to m into a. Fine. In the step number 2, what you have to do, you have now expressed this particular physical quantity in terms of any other physical quantities, like I have expressed force in terms of mass and acceleration. Now step number 2, you have to write down their SI unit. So mass SI unit is kg or kilogram, acceleration is meter per second square. Fine. You simply have to remember now that the SI unit of acceleration is meter per second square, and those of you do not know how it is meter per second square, we will see its details in the chapter called motion. Alright. Now we have written here it is kg meter per second square. As I have already mentioned you that in case of a dimensional analysis, you will always have it in terms of mass, length and time. Okay, you will have it in the form of mass, length and time. Mass means it is capital M, length is capital L, capital T stands for time. This is how we denote these three fundamental quantities. Okay, this is capital M, capital L, capital T. So we have kg. We have kg means we can say we do have mass over here. Okay, kg means we have mass. Now what is the power of kg? It is 1. So I will take here m to the power 1. Meter. So what is meter? We express it as capital Ly because it is length. Now what is the power of meter? We have it as 1. Now in the denominator part we have second square. Alright, so second square, second is time, time we denote in the form of capital T. Okay, so capital T, what is the power of second? We have it as 2 or it is square. So let us write down the power of capital T, same as 2. But one more thing, it's very important for you to remember, this is something to note for you, is that in denominator, in case of dimensional analysis, in denominator we always have 1. So what I have to do, I have to take the physical quantity present in the denominator to numerator. So how can I write this? I can write this as m to the power 1, L to the power 1, T to the power minus 2, and definitely I have to place them in square brackets. Okay, in square brackets I have to place them. Do remember, many students do not replace these physical quantities in the square brackets and hence they lose mark. In option you will be having option A. Okay, option A you will have m1 L to the power 1 to the power minus 2. There is no square brace. Alright, there is no square brace at all. And these questions are mostly asked towards the last of your question paper. Okay, when your question paper is about to end, you will find this kind of questions. And if the student is in a hurry, he will definitely go with option A, and there where you lose your marks. Fine. So do pay attention to the every nitty gritty, even an iota, whatever I am teaching over here. That's quite important for your examination. Well, so I hope this topic is clear to you. Now let us start with a very important topic, that is motion. Now under this motion we will be studying rectilinear motion. Now rectilinear motion is nothing different but it is known as motion along a straight line. It is known as motion along a straight line. That means if this is a point A and this is a point B and a body travels from A to B and A to B is a straight line. A to B is a straight line, then we can say that the body is under rectilinear motion. Fine. And in the later part of this, we will be dealing with the laws of motion, or simply we can say it is the Newton's laws of motion. Okay. So let us first deal with this rectilinear motion and then we will gradually come to Newton's laws of motion. So when we talk about motion, first of all, this motion is generally of two types. One we have is uniform motion, other we have is non-uniform motion. Many of you might be familiar with whatever I am teaching, but I am starting with the basics for those who at a zero level do not have an idea what is going to be asked in the examination. So I hope this will be helpful to everybody. So let us first start with this uniform motion. Now let us see what is uniform motion. Well, let us take an example again. So this is a point A, this is a straight path, this is point B, this is straight path, this is point C. Okay, now a body, so this is a particular body. Now this body travels from A to B. Okay, it travels from A to B. So the distance covered by this body from A to B is say 2 meter. Time taken is say 2 seconds. Again the same body is continuing from B to C and the distance covered is again 2 meter. The time taken is again 2 seconds. So we can see over here that the distance traveled by the body is same throughout, that is from A to B it is 2 meter, from B to C is also it is 2 meter, and the time taken by the body in first case is 2 seconds, in the second case is also 2 seconds. So what can we deduce from here? So it's quite reasonable to deduce that the distance traveled by the body is same throughout, that is from A to B it is 2 meter, from B to C is also it is 2 meter, and the time taken is also the same. That means the time period or the duration is taken is also same. That is from A to B it is 2 seconds, from B to C is also it is 2 seconds. Fine. So we have two conditions over here, that if a body covers equal distances, second is that time taken is also equal or at equal time interval or equal time interval, then we say that the body is under uniform motion. Alright, that the body is under uniform motion. Now, if a body fails to satisfy both these criteria, or say the body even satisfy, or even the body simply fails to satisfy even one among these criteria, then we say that the body is under non-uniform motion. Okay, that means in order to be uniform motion, the body has to satisfy both these criteria, that is equal distance and equal interval of time. If the body fails to satisfy even a single criteria, then we say that the body is under non-uniform motion. Alright, now if you consider the same path, say we have here the point A, this is my point B, and this is say point C. So if the body covers 2 meter from A to B and from B to C it covers 3 meter, and the time taken from A to B is 2 seconds and even from B to C it is 2 seconds. So what can we see from here? That the body satisfies the second criteria. Okay, the body satisfies second criteria, that is equal time interval. But does it covers equal distance? No, absolutely not. So the first point stands cancelled. In this case we say that the body is under non-uniform motion. Alright, so hope it is clear to you. Now let us get into some basic terms. So let us first understand what is called distance, and a related term to this distance is speed. Alright, and a related term to this distance is speed. Okay, so I have a point A over here and I have a point B over here. Now I have three possible ways to reach from A to B. One is a straight line from A to B. Other, as you can see, this is a curve or a curvilinear path from A to B. This is also a curvilinear path from A to B. Okay. So this is say Mr. X, Mr. Y and Mr. Z. Now Mr. X has to take this first curvilinear path. Mr. B or Mr. Y has taken this second path, and Mr. Z has taken this third path. Alright. Say Mr. X has covered 5 kilometer distance from A to B when he prefers first curvilinear path, and Mr. Y has just taken say 3 kilometer from A to B, and say Mr. Z has taken 4 kilometer from A to B. Fine. So how do we conclude that what is distance over here? So distance is nothing but the actual path covered by a body. Alright, so it is nothing but the actual path covered by a body. As you can see, Mr. X has covered 5 kilometer, Mr. Y has covered 3 kilometer, Mr. Z has covered 4 kilometer. So the path covered by them, by these three persons over here, is different. Yes, so that means the distance covered by them is also different. Okay, so it is the actual path covered by them. It's very similar happens with all of us. Yes, as you know that when you travel from your home to say your class, or you travel to from your home to your college, one may cover 5 kilometers, the other may cover 10 kilometers, and the other person, the third student, may cover even 1 kilometer. Alright, so it is nothing but the actual path that is covered by the body. Well, so a very similar term or a related term to this distance is speed. So let us see what is speed is all about. Okay. So this is the point A and this is my destination point B. Say X has covered this is point A and this is point B, my destination. This is my curvilinear path. This is Mr. X is say covering 10 meter. Okay, so Mr. X is covering 10 meter from A to, and Y is covering 5 meter from A to B, and Z is covering say 6 meter from A to B. Now say the time taken by X to travel from A to B is 5 seconds. Okay, so A to B has covered 10 meter in just 5 seconds. Okay, so in 5 seconds X has covered 10 meter. So in 1 second how much is traveling, or how much distance is it covering? It is 10 meter divided by 5 seconds. So 5, it is 2, so answer is 2 meter per second. Now what is its significance? That means Mr. X is covering 2 in every 1 second of time. Okay, so how can we write this in a generalized form? We can say that Mr. X is covering the distance, that is the entire 10 meter, divided by this time taken by 10. Okay, so this Mr. X, we have written it in a general form. Now this is nothing but known as speed. Okay, so we can say that speed is equal to distance covered by the body divided by time taken by the body. So what is the speed of Mr. X over here? It is 2 meter per second. Fine. So speed is equal to distance per unit time. Now what is the SI unit of distance? It is meter. What is the SI unit of time? It is second. So what is the SI unit of speed? We have a division symbol in between. So it is meter per second. So the SI unit of speed, SI unit of speed is meter per second. Fine. I hope it is clear to you. Now let us see whether speed is a scalar or a vector quantity. Okay. Now as we have already defined, distance is the actual path covered by the body. Okay. Okay, so distance, when we say distance is the actual path covered by the body, we saw Mr. X has covered 10 meter, Mr. Y has covered 5 meter, Mr. Z has covered 6 meter. That means there is no fixed direction to define the distance. So ultimately what happens is that distance becomes scalar. And as we all know, time is a scalar. We do not need direction to define time. Alright. There are so many, I think there are quite few students who define it in terms of like Newton. So that is time has a direction. That's a different aspect. We are not dealing with your astrophysics. That comes in the part of astrophysics when you consider time as one of time with respect to direction. So leave that. We are only focusing on general physics required for your examination. Alright. So distance is a scalar, time is a scalar. So speed will also be a scalar quantity. Alright. So speed is a scalar quantity. Okay. Fine. So now let us understand another term. Well, now let us deal with another term, that is displacement. Okay, displacement. Now it is defined as the shortest distance from initial position to the final position, from initial position to the final position of a body. Okay, defined as the shortest distance from initial position to the final position traveled by a body. It's not off over here. Traveled by a body. Traveled by a body. Okay. Now never say it is the shortest distance between 2 points. No, never. Say this is point A, this is point B, and we all know that the shortest distance is always a straight line. And say from A to B it is 10 meter. So the here displacement becomes 10 meter. No, never say that the shortest distance between 2 points. So it is always from initial position to the final position traveled by a body. How? So this is a body I am having. So initially it is at A. Okay, initially it is at A. Now it is traveling 10 meter and reaching point B. Now from B again it travels back to A. That means I can say initial position and final position of this body are same. When I say initial position and final position of the body are same. Now what is the shortest distance from point A to point A? It is 0. So in this case the displacement of the body is equal to 0. Okay, but if the body would have stopped at point B, that means the final position is point B, then you can very well say that the displacement is 10 meter. That's a quite safe answer over there. But here you cannot say, because the initial and final position are the same, and since the body is returning back to its initial position and the distance or the displacement between A and A is 0. Alright, or the distance traveled from initial to final position becomes, and the shortest distance between this point A and point A is 0, so displacement is 0. Alright, so hope what is displacement is clear to you. Now similarly, as you have seen speed related to distance, now we will see what is velocity. Velocity is related to displacement. Now let us understand what is velocity. Okay, this is point A, this is point B. Okay, so the body is traveling along a straight line from A to B. This is my initial position, this is my final position, and the displacement is 10 meter. Why displacement? Because it is a straight line, that is the shortest distance from my initial position to the final position, it is 10 meter. So the time taken by the body to cover this 10 meter is 2 seconds. Okay, so that means in 1 second how much the body is covering displacement, or what is the displacement of the body in 1 second? It is 10 meter divided by 2 seconds, so it is 5 meter per second. Okay, it is 5 meter per second. So how can you write this? So it is velocity can be written as displacement per unit time. Now, as you have observed that I was continuously focusing the shortest distance is always a straight line. That means the direction from initial position to the final position is fixed. It is always a straight line. I cannot take a curvilinear path. No, I cannot take a curvilinear path. Alright. So it is always a straight line. That means the direction is fixed. So what can I say? Displacement is a vector quantity. So I have to represent this by an overhead arrow. Alright. So time is a scalar quantity. Alright. So since we have numerator is a vector, denominator is a scalar. So the physical quantity velocity will be a vector quantity. Okay. So velocity is a vector quantity. We denote velocity as small v with an overhead arrow. Alright. So we can write over here that velocity is equal to displacement per unit time. Fine. So hope it is clear to you. Okay. Now let us deal with, since the basics of motion is clear to you, now let us deal with something known as equations of motion. Now from an examination point of view, you might face a single very simple numerical problem from whatever we have learned now. You might face, there is quite less possibility. Alright. So since I don't want to ignore any of the angles, so I'm covering this topic as well in a crash course. Okay. So you don't have to go to its derivation. I am not doing any kind of derivation over here. First of all, the derivation of equations of motion involves differentiation and integration. Alright. So that may not be understandable by many. And also the derivation is not at all required from examination point of view. Simply you have to remember the formulas, that is important. I'll write down the formulas and then I'll tell you what is the notions of it, or what is the notations of those symbols. So first equation of motion we have V is equal to U plus AT. Second we have S is equal to UT plus half AT square. Third we have V square minus U square is equal to 2 AS. Okay, so these equations of motion are applicable to only a body traveling along a straight line, or the body when it is applicable to a body when the body is under rectilinear motion. Okay, so motion along a straight line is known as rectilinear motion. So we are dealing here with the rectilinear motion. Okay, so here V stands for final velocity, U stands for initial velocity, A stands for acceleration, T stands for time, and S stands for displacement. Why displacement? I am saying why not distance? Because we are discussing rectilinear motion. That means motion along a straight line. That means when a body is traveling in a straight line, we say that the body is under rectilinear motion. Straight line means it is the shortest distance. Okay, so shortest distance means it is displacement. So here we can say that distance covered by the body is equal to displacement of the body. Okay. So now a very popular question that may be asked in your examination. It is almost asked in every examination. Okay, and often the question is also repeated, so I'll be discussing that question, which will be fruitful to you. Okay, fine. So this is a surface. This question has been asked many times in various examinations, so I'm repeating this question because this question is repeated. So this is a building. Do not mind my drawing because the graphic pad has some issues. So this is a building. Okay, I'm having a building. Say H is the height of the building. A body is released from here, and say the acceleration due to gravity small g. I'm considering this. This is actually 9.81 meter per second square we take, but for the sake of calculation, I take it approximately equal to 10 meter per second square. Okay, fine. Now, say the time taken by this particular body to reach the bottom surface, that is to the ground, is say 2 seconds. Okay, the time taken by this body to reach, or this ball to reach to the surface, is 2 seconds. I am determined to find out the height of the building. Okay, I am determined to find out the height of the building. Well, now the distance or the displacement of this body is nothing but equal to the will be equal to the height of the building. That means that the displacement is S over here. Okay, the displacement is S. So that means the displacement of this body is equal to height of the building. So I can say S is equal to H. So if I find out the value of S, so that will be equal to my H. So I know the acceleration due to gravity as small g, almost equal to 10 meter per second square, time as 2 seconds. So if I am writing here which equation I can use, I would be using the second equation of motion, that is S is equal to ut plus half at square. Okay, so it is half at square. So initially the body is at rest, so u value will be 0. So 0 into t will give me 0 plus half. Now what is the acceleration? Acceleration is due to the gravity, so it is into 10. Now what is this? This is t. Time is given as 2, so it is 2 square. So it will get cancelled. 10 will get cancelled by 2. It is 5 into what is the square of 2? You have 4. So answer is 20 meter. Okay, so this is nothing but equal to S, which is equal to H. So what is the height of my building? The height of my building will be 20. Okay, so hope this is clear to you. I have just shown an application of the equations of motion that was already asked. This is already asked in your examination. Okay, so hope it is clear to you. Okay, now let us discuss about very important. This is Newton's laws of motion. Okay, so Newton's laws of motion, we have three laws. The first law is known as law of inertia. Second law is known as the real law. This is the second law. And third law deals with action and reaction. Okay, so now let us deal with The first law, or the law of inertia. So law of inertia or defined as the first law. Alright, so let us first understand what is this inertia. Inertia is nothing but the tendency of a body. Tendency is nothing but, again I can simplify this term as the nature of a body. Okay, it is defined as the nature of a body. Alright, so now what is this tendency or nature? So this is a body. Now this body is at rest. Now how long this will be in rest? This will remain in rest until you apply some force to it. Okay. So the nature of the body is to remain in rest. Say if this body is under uniform motion. Uniform motion. That means the tendency of this body is to always remain in motion. Okay. So to always remain in motion. Alright. Now let us see what is the first law states. Now Newton's first law states that if a body continues to be in its state of rest or in uniform motion unless and until an external unbalanced force acts on it. Alright, it states that a body continues to be in its state of rest or in uniform motion unless and until an external unbalanced force acts on it. That means if a body is at rest, it will always remain in rest. If a body is in uniform motion, it will always remain in uniform motion unless and until an external unbalanced force acts on it. Alright, so now let us see, this is nothing but Newton's first law. Quite theoretical in nature, we do not have any mathematical derivation for this particular concept. Alright. So now let us understand what is known as inertia of rest and inertia of motion. Okay. Now inertia of rest. So this is a body. Inertia of rest. Say this is a body. Alright. Now this body has two parts. This is the upper part. This is say lower. Okay. Or say let me explain you in this way. Or say if I explain you, this is a person, okay, so this is a man, and this man is now sitting on a particular seat. Alright, now he's sitting on a car, okay, he's sitting in a car. Now the car starts moving. Initially the car was at rest, so what will happen, the upper part of this body will remain in rest and the lower part of the body is in contact with the car's seat. So what will happen? The lower part of the body will also try to move along with the car, but the upper part of the body is at rest. So what will happen? We'll experience a backward jerk. Alright. Now what was the tendency or the inertia of the body here? The inertia or the tendency of the body was to remain in rest. So this is an example of inertia of rest. Inertia means simply it is the tendency. The tendency of the body was to remain in rest. So it is an example of inertia of rest. Fine. Now let us see what is known as inertia of motion. What is called inertia of motion. Okay. So under inertia of motion, say this is a person. He is sitting on some moving vehicle. Now this vehicle is in motion. Now what happens? Suddenly this comes to rest. When suddenly it comes to rest, the lower part of this body, as you can see, the lower part of this body will also try to come to rest along with this vehicle. Fine. The lower part of the body will also try to come to rest along with this vehicle. But what will happen to the upper part of the body? The upper part of the body cannot cope up with the lower part of the body, and it will tend to remain in motion. What was the tendency of the body? The tendency of the body was to remain in motion. So what will happen? The body will continue to remain in motion. Alright, so this is an example of inertia of motion. In order to understand, in order to know whether the body is in inertia of rest or in inertia of the motion, you have to know what is the tendency of the body. Whether the tendency of the body was to remain in rest or the tendency of the body was to remain in motion. If the tendency of the body was to remain in rest, the answer will be inertia of rest, and if the tendency of the body was to remain in motion, the answer will be inertia of motion. Hope this is clear to you. This was all about first law. Nothing much to discuss over here in the crash course. So coming back to the second law. So second law is known as the real law. Alright, so second law is known as the real law. Say, just a minute. Yes, the momentum is a vector quantity. Fine. Now, impulse is defined as the rate of change of momentum. Okay. Impulse is defined as the rate of change of momentum. Alright. Now impulse will denote this say by capital I, since it is rate of change of momentum. Now what does this means? So this is a body. I am having a body. Now this body is having mass m. Okay. Now I am applying some force to it. Initially, say the body was moving. Initially, it is moving with a velocity v1. Now when I apply force to this body, what is going to happen? Is it mass going to change? No, mass will remain constant, but what is going to change? Velocity will be changing. So the velocity will change to v2. Okay. So what can I say? How can I say that the change in momentum? How can I express the change in momentum? Change in momentum can be expressed as final momentum minus initial momentum. So final momentum is m into v2 vector, final initial is m into v1 vector. So this is nothing but known as change in momentum. Say in order to have this change, the time taken is t. So in 1 second, how much change is occurring? It is divided by t. So this is nothing but known as the rate of change of momentum. Okay, this is known as the rate of change of momentum. So what can I say? If my force, if I am applying more force, if my applied force is increasing, what will happen to my rate of change of momentum? What will happen to rate of change of momentum? rate of change of momentum will also increase. Rate of change of momentum will also increase. That means I can say that the force applied on a body is directly proportional to the rate of change of momentum of that body. Yes, fine. So in this case, or in the second law, Newton stated that the force applied on a body is directly proportional to the rate of change of momentum of that body. Now let me express this mathematically. Okay, so mathematically how can I write? This is F vector is equal to d p vector by dt. I've written this in differential form. dp means it's very small change. The change is quite small. dt means there is a very small change in time. That means there is a small change in momentum with a small change in time. So now how can I write this? I can write this as F vector as m into v2 vector minus m into v1 vector divided by change in time, that is dt. So I can write this as again m vector. If I take f vector, if I take m common, I have v2 vector minus v1 vector. v2 vector minus v1 vector divided by dt. So this can be written as f vector as m into, so this change in velocity, this is nothing but v2 minus v1 is change in velocity divided by small dt is change in time. How can I write this term? I can write this term as acceleration. Okay, I can write this term as acceleration because we defined acceleration as change in velocity with respect to change in time. Okay, so this is acceleration. So how can I write f vector is m into a vector? Okay, so it becomes vector because this is a scalar, this is a vector, so scalar into vector, I got it as a vector. Okay, now so force is a vector quantity. Do you remember in the dimensional analysis I told you about force, where I written force is equal to mass into acceleration. Now let us see what is the SI unit of force. We know SI unit of mass is kg, SI unit of acceleration is meter per second square. So the SI unit of force is kg meter per second square. So since Newton has defined force in his second law, so we name this SI unit in the name of Newton and denote it by capital N. Okay, so we can write here that 1 kg meter per second square is equal to 1 Newton. 1 kg per meter square is equal to 1 Newton. Okay, so the SI unit of force is Newton. Is it clear? I hope it is clear to all of you. Since I am unable to see your comments, the chat section has been disabled. I do not know, there is some kind of technical error. I hope. Okay. Now coming to Newton's third law. Alright, coming to Newton's third law, it deals with action is equal to minus reaction. Now action and reaction are both are equal in magnitude but different in direction. Since it is a force, so we have to definitely, this force is a vector quantity, so we have to express it in terms of magnitude as well as direction. Okay. So what does Newton's third law states? For everybody might be knowing, for every action there is an equal and opposite reaction, but that is an incomplete definition. The definition states that for every action there is an equal and opposite reaction acting on two different bodies. Okay, so Newton's third law states that for every action there is an equal and opposite reaction acting on two different bodies. Okay, so it has to act on two different bodies. Alright, action and reaction can never be on the same body. So what do we conclude from this law? This is a law. We conclude that forces always exist in pairs. Alright, forces always exist in pair. Why? Whenever there is a force, it will always be treated as action. If there is an action, there has to be a reaction. Alright, if there is an action, there has to be a reaction. Say, this is a body A, this is another body. If A is applying a force on B, so this is my action, definitely B has to apply a force on A, and that is my reaction. I have to denote by a negative sign because it is the opposite to that of the direction of applied force or action. So both A and R, that is action and reaction, will be equal in magnitude but opposite in direction. So A is equal to minus of R. Alright, so very important application of Newton's third law we have is conservation of linear momentum. Conservation of linear momentum. Now, conservation of linear momentum is an application of Newton's third law of motion. Now, let us understand what is this conservation of linear momentum. Hope this simple statement action reaction is clear to you. Alright. Law of conservation of linear law of conservation of linear momentum. Law of conservation of linear momentum. Okay. So now law of conservation of linear momentum is applicable to an isolated system. Now what is system? Let us consider. See. Let us see here what is a system. This is a body A. This is a body B. Mass of the body is m1. Say initially this body is moving with a velocity say u1. This is body 2. The mass of the body B is m2 and it is moving with a velocity u2. Now if I say u1 is greater than u2, then what will happen? These two bodies at some instant of time will definitely collide. Yes, this is my body A and this is my body B. And after collision, what will happen? There will be a slight separation between these two bodies, irrespective of the matter whether both will roll in the same direction or in opposite direction. That is none of our concern. But this is for sure that there will be a slight distance between the bodies. They will slightly separate away from each other. That is sure. Okay. Say after collision, so what is happening? Say after collision. So during this is my scenario before collision. So this is before collision. And this particular scenario is during collision. And this is same body A and body B, and this is after collision. Okay. Now if I ask you what is the total momentum of this system, now system is a part of the entire surrounding on which our focus is concerned, or on which we carry out experiment. Right now we are simply focused on these two bodies, that is A and B. So what is the total momentum of this system before collision? So before collision, the total momentum of this system is momentum of A plus momentum of B. What is the momentum of A? It is m1 into u1 plus momentum of B, it is m2 u2. So the total momentum of the system is m1 u1 plus m2 u2, and this is after collision. Now what is the momentum of after collision? Say the mass after collision. Do you think the mass will change? No, the mass will never change after collision. Mass will always remain constant. Then what is going to change? The velocity will be changed. Say after collision, the velocity of body A is v1 and body B is v2. Okay. So what is the momentum of the system after collision? It is momentum of A plus momentum of B. So it is m1 v1 plus m2 v2. Now law of conservation of linear momentum states that the initial momentum before collision is equal to final momentum after collision. Okay, initial momentum before collision is equal to final momentum after collision. That means this can be written as m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. Okay, so this is the basic law. Now let us see how initial momentum is equal to final momentum. All right. So this is my body A and this is my body B. Now this is a scenario during collision. Alright, so this is the scenario during collision. Now body A during collision, what is happening? Body A is applying some force on body B. Yes, and B will also in return apply some force on body A. So that is nothing but A is applying force, that is action, B is applying force, that is reaction. We know action is equal to minus of reaction. Now let us see how much force is being applied by body A on B. That is nothing but the rate of change in momentum of body A, as we have seen in Newton's second law of motion known as real law. So it is nothing but final velocity v1 minus u1 divided by t. Now what is this t? This t stands for time of collision. Now both the bodies are colliding at the same time. That means the duration of this collision will be same for both the bodies. Say the collision has occurred for 2 nanosecond or say 2 microsecond. The duration for which the collision is occurring is same for both the bodies. So the force applied by A on B is V minus U1 by T. So this is nothing but the rate of change of momentum of the body. Alright. So now this can be written as what is the force applied by B on A. So this is minus, why? Because action is positive, reaction we are taking this to be negative. So this is minus V2 minus U2 divided by T. Okay. So since time taken by both the bodies is same during collision, that is collision is occurring for a particular duration of time for these two bodies. So T and T both are same, they will get cancelled out. Alright, so I have here as V1 minus U1 and this is minus V2 minus plus U2. So since it is the rate of change of momentum of the body is directly proportional to the force applied, so this is my acceleration part. I am multiplying with the mass of this body. So the mass of body 1 we have already considered this to be m1, and the mass of the body B we have considered this to be m2. So this is here, as you can see in the general format for rate of change in momentum, this is m into change in momentum by time, m into change in momentum by time. So this I am multiplying this with m1 over here and this particular minus v2 plus u2 with m2. Now if I simplify what I am having here, m1 v1 minus m1 u1 is equal to minus m2 v2 plus m2 u2. Now I'll take all u terms to one side and all v terms to another side. So in LHS, that is in the left hand side, I'll have all u terms, and in the RHS part I'll take all v terms. Okay, so in LHS, if I'm taking all u terms, how can I write this? I can write this as m1 u1 plus m2 u2 will be equal to m1 v1 plus, just a minute, there is no space over here, let me write it here. Let me write it here, there's some problem. Okay, yeah. So I'm writing it here. So I can write this as m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. Okay. So finally, this is how we derive the equation for law of conservation of linear momentum. Fine. So I hope it is clear to you. Whatever I have taught till now is quite important. So do go through this video once again after it has been uploaded, and you can make your own notes. That will always help you, because writing helps you to remember a lot, and also you will face your own difficulties while you write down the stuff by yourself. Alright, so I request each and everyone watching this video to go through it once again once this has been uploaded, and take your own notes. So that's it for today. I wind up with here. We'll meet in the next class. Thank you for joining us.